Hello everyone, I hope you're doing well. In this video, we are gonna calculate the planar density for 112 plane in simple cubic structure. Yeah, this is a different kind of plane and it's really interesting. Let's quickly get started with the solution. Let's see how we can do that. The first thing that we need to do is to draw the plane inside the cubic structure, and after drawing it, we'll use the formula that will guide us to calculate the planar density. And let me first write the formula here because that is important. So planar density, this formula is general and it could be used everywhere, okay, for every structure that you are considering. So planar density is actually equals to capital N divided by A, and capital N is actually the net number of atoms centered on the plane divided by the area of the plane. And this word centered is really important. All those atoms are considered as part of the plane whose centers also lie on the plane. Okay, we'll see later on how this works. And this is the formula that we are going to use, and I'm going to use this sigma sign to represent planar density, and that is equals to capital N divided by A. Alright, let's draw the plane first and then we'll calculate the area of the plane and then we'll calculate the number of atoms. Let's do that. Let me first draw the plane on the paper. So this is cube. Okay, first of all we need to draw the cube inside which we'll draw the plane, and next is to identify the coordinate system. And we can see here that all of the indices are positive here, so we'll choose a all positive origin, which is this point. Okay, all positive origin, I refer to this point, I refer this point to be as the all positive origin, and the reason is because when all of the indices means x index, y index and z index, all of them are positive, then we choose this point as our origin, and correspondingly this point, this axis line as x-axis, this is y-axis, and this is the z-axis. In case when any of the index is negative, we have to shift the origin to ensure that our plane is drawn inside a single unit cell. If we do not shift the origin, if we take this point for example as origin, then what happens is you have to draw multiple unit cells in order to draw the plane completely. So this is not something that we want. We don't want to complicate the process and drawing, and that is the reason we shift the origin and we choose the origin that makes the drawing process way easier. So that is why we have to keep this in mind, that whenever the indices are negative we have to shift the origin. So this is a coordinate system. We can see here the axis lines are really important in drawing the plane. So now in rough work we'll see what are the intercepts of the plane, of this plane. In case of directions we get position coordinates from Miller indices, while in case of planes the Miller indices tells us the intercepts of the plane. Intercepts are the point where the plane touches the axis line. These are the axis lines. These three are the only axis lines, and the point where the plane cuts them or touches these axis line is called as intercept. That's an easier representation of planes. So in rough work we have 1, 1, 2 as the three indices, x index, y index, z index. Taking inverse will give us the intercepts. Inverse of 1 by 1 is 1. Inverse of 1 is again 1. Inverse of 2 is 1 by 2. Inverse means dividing it by 1. So 1 by 1, 1 by 1 and 1 by 2. Okay, so 1, 1 and 1 by 2 are the final intercepts. This is x-intercept, y-intercepts, and this is the z-intercept. Now x-intercept is 1. How to take it? X-intercept is 1. It means starting from origin. 1 means 1 from one corner to the other corner of the unit cell. So that is something 1 means. Half, 1 by 2 means halfway. 1 by 4 means half of half, this way, and so on. Okay, we are taking them like that, depending upon from corner to corner along axis direction. This length is not a, like this length is not 1, like from this corner to this corner, this length is not a, only along axis direction, those corner to corner which are parallel to axis lengths. So from this corner to this corner, from this corner to this corner, these are parallel now, so they will be taken as 1, but all other directions will not be, only those which are parallel to axis direction. So starting from origin to the other corner of the unit cell along x direction, since x intercept is 1, so this is a point on the plane, as you can see. And next we have 1 as y intercept as well. So in case of intercept, what we do is we always start from origin. So it will not happen like if a y intercept is 1 and we are like starting from this point along y direction to the other corner. No, this is not the point, but starting from origin again, all over again. In case of infinity, the situation becomes a bit different, because infinities are taken by definition differently and they convey different information, but all other cases will remain the same, like we will start from origin every time when we are drawing the intercept, taking the intercept points. Starting from origin to the other corner of the unit cell along y direction, this is the point. This is the point on the plane. Next is half, 1 by 2 along z direction. So starting from origin, this point is the point 1 and half of it will give us 1 by 2. So this point, this here is the half of this whole length. So this is the point on the plane. Now let's join these lines together to get the plane. All right. If you notice here, this is a isosceles triangle. Oh my god, what are the spellings? So there is one more s here. This is the spelling, right spelling. This is a isosceles triangle. This plane forms a isosceles triangle. Why I say this? Because this length and this length are equal to each other, though they don't look like in the figure that I have drawn, because the figure is not accurate in terms of lengths I have taken, but we can justify it right now. You can see this length. What is this length? This is a, okay, and what is this length? This is a by 2. We know that because it's half. This whole length is a and this is half. This is a by 2 and this is a. We can use Pythagoras theorem to determine this length. Let's determine this length by Pythagoras theorem, because we would need these lengths later on as well. So why not to you calculate it right now? Let me call this point as A, this point as B, this point as C. Okay, this length is A, this length is A by 2, this length is A also. So we can determine these hypotenuse lengths just for confirmation. This hypotenuse is AB actually now, and that is its square. Hypotenuse square equals A square plus A by 2 whole square. So it's A square plus A square by 4. Taking A square common, 1 plus 1 by 4, which is equals to A square 5 by 4. You can take the LCM. Taking under root on both sides, it gives AB length equals under root 5 by 4 A. Okay, this is the AB length. Similarly, we can do it for this BC length. Okay, for it will be the case like BC squared will be equals to A square plus A by 2 whole square. The same situation, it will give the same result. Hence, we can say that AB length is equals to BC length, that is equals to under root 5 by 2 into A. Under root of 4 will be 2 now, that is why I wrote it like that. So the lengths, this these lengths are under root 5 by 2a, this length is under root 5 by 2a. And what is this length? We have already done it for multiple videos. This length is a, this length is a as well. We can determine this length by using Pythagoras theorem again. So it will give us c square, let's say this length is c, equals a square plus a square, which is equals to 2a square, and taking under root on both sides gives c, which is equals to under root 2 into a will come out of the under root, so because it's square on it, c equals under root 2a, this is under root 2a. We can see these two lengths are equal, but the third one is not equal, and this is a isosceles triangle. Now we need to find two things in order to calculate the planar density. One is area, the second is the net number of atoms per unit cell. And now one more thing that I first of all will find out the area, secondly we'll determine the net number of atoms lying on the plane. And let me add one more thing here so that it is clarified already, since we can see that this is the line BC and this is CA and this is BA and this is AC. This length is same and AB, and in that case this is also length AB and common side, since they both represent similar situation, that is why the angle here and here will be same. Okay, you can see here, let's say this is under root 2a by 2, under root 2a, same side lengths, and it's a isosceles triangle as well. So these two sides are equal and these two sides are equal, so the angle will be equal as well, while this angle, the third angle, will be different. Okay, but these two angles will be same. To find out the area of the plane, we need to know only one angle, and we'll calculate this angle for the area calculation, and only that angle information will be needed to calculate the net number of atoms lying on the plane. So let's quickly determine this angle. And here what we want to do, we already know these lengths. Okay, we know all of these lengths, we just need to know this angle. I write the formula that we'll be using here for this isosceles triangle. So to calculate this angle, I'm gonna use the dot product thing. We'll treat them as vectors. For example, this is a vector in this direction and here we have another vector like that. Okay, in dot product we know the angle between the tails is, let's say, alpha, and this is, let's say, a small a vector and this is small b vector, and a dot b is equals to ab cos alpha. And if we do this thing where a and b are the magnitudes, so cos alpha, and taking the cos inverse of both sides will give us the alpha angle, which is the angle between these two vectors. And we want to find out the angle between these two vectors, between their tails. That is why I took the other point as head. Okay, so this thing will help us to find out the angle really easily. So but we need to know these vectors first. What are these vectors? This is tail and this is head. Tail to head is a vector. First tail coordinate, then head coordinate. This is one of the vector, and another vector is tail head, which is CA. And this vector is given by B coordinates minus C coordinates. Head coordinates minus tail coordinates gives us the vector coordinates. So similarly here head is at A, so A coordinates minus C coordinates. Now we need to know the coordinates of A, B and C, and for that purpose that's really easy. We know that what is the location of point A. Location of point A is 1 unit motion along x direction, 0 motion along y and 0 motion along z. Coordinates of B is 0 motion along x, 0 motion along y, 1/2 motion along z. That is really easy. Similarly, coordinates of point C is 0 motion along x, 1 motion along y, 0 motion along z. These are the coordinates. If we will write I hat, j hat and k hat, with them, it will convert them into vector, but we'll treat them in terms of coordinates here to make the process really direct. So B coordinates are this one 0 0 1 by 2 minus C coordinates, which is 0 1 0. Let's subtract corresponding x to x, y to y, and z to z. Okay, we'll not mix them, we'll write them in brackets again. So 0 minus 0 gives 0, 0 minus 1 gives minus 1, 1 by 2 minus 0 gives 1 by 2. So this is what we have got, and we also need their magnitude because we will divide them. So we'll calculate its magnitude right away. Its magnitude is 0 square minus 1 square 1 by 2 square. We take the square of each of the coordinate and take the under root. So it's 0 plus 1 plus 1 by 4, and it's under root 5 by 4 that we already knew, multiplied by a gives the side length in terms of a. But okay, so these are the two things that we now know already. We need to know now the second length, which is CA. That is super easy to calculate as well. Let's do that. CA equals A minus C. Okay, A, for A point we have 1 0 0 coordinates minus C, which is 0 1 0. Let's subtract them. 1 minus 0 is 1, 0 minus 1 is minus 1, 0 minus 0 is 0. So and now the magnitude, it's under root 1 square plus minus 1 whole square plus 0 square, that is equals to under root 2. Alright, now let's put them into this formula. We have CB vector dot CA vector divided by CB vector magnitude CA vector magnitude, that is equals to cos of theta. Theta is this angle that we want to calculate in order to calculate the area of the plane. So let's put the value. I'm writing cos theta right here. CB vector was equals to this. We'll write them like that, dot, then we have CA vector, which is this 1 minus 1 0 divided by their magnitudes product under root 5 by 4 under root 2. So it's cos theta equals, taking the dot product, which means 0 multiplied by 1 is 0, then plus sign. Okay, now we'll not write the commas, we'll write the plus sign because we are taking the dot product. 0 into 1 gives 0, minus 1 into minus 1 is plus 1, plus 1 by 2 into 0 is 0, divided by under root 5 by under root 4 is equals to 2, so I'm writing under root 2 here. Sorry, under root 4 is 2, so I'm writing 2 here, multiplied by under root 2 here. Then we have, let's wait, there's another page. Wait. So we are left with cos of theta equals 1 over under root 5 multiplied by under root 2, and this 2 goes right here. It's cos theta equals 2 over under root 5 multiplied by under root 2. Theta would be equals to cos inverse of 2 divided by under root 5 into under root 2. Okay, let us calculate it using calculator and see what the angle is. It's 2 divided by under root 2. Use brackets when we have multiple terms. Cos inverse of this thing, it's 50.76847952. This is accurately the angle, which is 50.7685 degree. This is the angle here. Now area of the plane, triangular plane, is equals to 1 over 2. Let me show it to you people. 1 over 2 into BC and AC, between which we calculated the angle, okay, the sides between which the angle we took. Okay, these are the two sides now, CA and CB. So CA length into CB length with A in it, we will multiply A as well, sine of angle between them, which is theta. So this is the formula 1/2 CA length. What is CA length? The CA length was under root 2 into A. We'll take A as well because all of the parameters are in terms of A. A has to be multiplied at the end, whatever it is. So CB is this length, which was under root 5 by 2A. I'm writing it here. Sine of theta 50.7685. Alright, so let's calculate it and see what the area comes out to be. We can do some simplifications even here. A square multiplied by under root 2 under root 5 by 4 sine of 50.7685. This is the angle accurately, so I'm taking sine of this thing. It gives this multiplied by under root 5 under root 2 divided by 4. So this one thing, it's 0.6124 if you round it off A square. This is the area. So far we have calculated the area and the theta. Now we are going to calculate the number of atoms that are centered on the plane. Alright, so for that purpose I'm going to draw the plane. Alright, and we saw that this is the angle theta and this is the angle theta as well. Alright, so this is a simple cubic structure as well. Let's see what are the number of atoms, the total number of atoms that are centered on the plane. Now by center, what does it means? We only include those atoms, okay, those atoms contribution to the plane whose center also lie inside the plane. Okay, all those atoms whose center doesn't lie inside the plane are not included. Alright, so we'll see that how it happens in here, and the similar thing happens with the body centered atom of 111 plane in body centered cubic structure. We don't include the center atom because the center of that center atom doesn't lie on this plane, and that is why we are not including it. So only those atoms are added and their contribution are considered inside the plane whose centers also lie inside the plane. So we can see here that we have an atom here, okay, and we have another atom in here. At each of these corners we are only including those atoms which are potentially lying inside this plane. So we have these two atoms. Now the atoms that is lying in here, we can see that the plane is here and there is a no chance that the plane passes through this point, and hence this is the center of this corner atom and that doesn't lie on this plane. That is why this atom is not going to be considered. Only these atoms will be considered. Alright, so we'll consider only these two atoms contribution to the plane and none of the other atom is lying on this plane. And we have seen that why this atom is not included, because we can see that this atom's center is at this corner point and there is a no chance that this plane passes through this center point. Okay, if the atom's center is not included in the plane, hence the atom will not be considered as a part of the plane. Okay, and we can see here that here is the center of this atom and the plane is also passing through this point, and this point is a part of this plane. That is why we are considering this atom's contribution as well as this atom's contribution. None of the other atoms will be considered because their centers are outside of this plane. Alright, so in order to find out these atoms contribution to the plane, what we do here is to divide the theta that we have with the total angle of the circle. Okay, because we can see that only this part of the, this is the whole atom, and we can see this only this part of the atom is inside this plane, not all of it. So we have to find out the part that is inside the plane. Okay, and for that purpose we need to divide this theta with the total angle of the circle, which is 360. Okay, and we have this theta angle over here, so we'll divide 50.7685 by 360, and we'll get the atoms, this atom's contribution to the plane. And we can see that the same theta is here, so it will have the same contribution as this atom. It's 0.141. Okay, so this is this atom's contribution to the plane, and the same result will be obtained for this atom. So the net contribution is actually 0.141 for this atom plus 0.141 for this atom. All right, and that is actually equals to 0.282. all right, that is the net number of atoms centered on the plane, and we have this area. Now let's divide them both to get the planar density for 112 plane in simple cubic structure. Hence the planar density for 112 plane is equals to n over a, and we have n to be 0.282, and that is divided by the area that we got, which was 0.6124 a square. So let's divide them both, and the result that we get after dividing these quantities together is 0.461 by a square. That is the planar density in terms of lattice parameter a, and we can convert it into the radius of the atom making up the simple cubic structure. We can do that using the relation that actually a is equals to 2r, and we can put the value of a right here to convert, and it's since a is 2r, a square will be equals to 4r square. So we can simply put here 0.461 divided by 4r square, and we can even simplify it. Let me calculate what is 0.461 divided by 4 to get the simplified form. It's actually 0.115. all right, so this is the planar density in terms of radius of the atom, and this is the planar density in terms of lattice parameter. So this is it for this video. Additionally, it has the units of atoms per meter square, or you can write it as atoms, then space, and per meter square. all right, because we can see there is a area or the L square units in the denominator, so it's per meter square. And whatever results you are getting, for example, if you are given with a some value for a, you get maybe 4 multiplied 10 to the power 20, so you'll write atoms per meter square as its units. all right, so that is it for this video, and keep watching. If you have any queries, you can ask me, and let me know if you want any other video on such topics. And yes, goodbye.